Welcome to my channel. In this video, we will learn about structural effects. So, as far organic reactions are concerned, there are some sites of the reaction. At the site of reaction, whether your electron density is rich or deficient, or the site of reaction is electron rich or deficient, depending upon that, we have different organic reactions at that particular site of reaction. So here we will discuss about the organic reactions here, and those reactions on the basis of different structures we have different rates of that particular reaction. Suppose we take one example here, that is addition of HBr across this carbon-carbon double bond of ethylene. We get CH3 CH2 here, that is ethyl bromide. Another example, if you take CH3 CH double bond CH CH3, that is 2-butene. Again, addition of HBr across the carbon-carbon double bonds of your 2-butene, we get CH3 CH Br CH2 CH3. So this 2-bromobutane as a product. So in both the cases we have addition of HBr across the carbon-carbon double bond of our alkenes, and here it was observed that this is going to react slower than your 2-butene, or 2-butene react faster to HBr, or addition of HBr across 2-butene is faster than the addition of HBr across ethene. So here in those two particular examples, in case of 2-butene, this carbon-carbon double bond is electron rich as compared to the carbon-carbon double bond of this ethylene molecule, and therefore this is going to react faster than that of a ethylene molecule. This is because of change in structure. We have additional two CH3 groups attached to the carbon-carbon double bond. Here in the first structure, we do not have any such type of group attached to the carbon, and because of those CH3 groups, the electron density at this carbon-carbon double bond is going to be increased, and therefore it reacts faster with the HBr. As we know, this is the electrophilic addition across carbon-carbon double bond. For that purpose, your carbon-carbon double bond should be electron rich, and then your reaction becomes faster. Another example we take, that is aromatic electrophilic substitution on phenol and nitrobenzene. Let us take an example of bromination, addition of Br2, or sorry, substitution of Br2 on this aromatic ring. So here, when you have phenol as a substrate and bromination of this phenol, we end up with the formation of product, that is 2,4,6 tribromophenol. 2,4,6 tribromophenol. Whereas when you have bromination of this nitrobenzene, we end up with the formation of 3-bromo nitrobenzene. 3-bromo nitrobenzene. So this bromination of phenol as well as nitrobenzene, we come to know that at the time of phenol as a substrate, you have huge bromination of your aromatic ring. We end up with the formation of 2,4,6 tribromophenol as a product, and while if you have nitrobenzene as a substrate, bromination end up with the formation of 3-bromo nitrobenzene. So we say this is going to be slow reaction and this is going to have faster reaction. So we have huge bromination of this phenol as compared to nitrobenzene, and therefore what we can say, this is also one of the aromatic electrophilic substitution type of reaction, and during aromatic electrophilic substitution reaction, if your aromatic ring is electron rich, then the electrophilic substitution become more facile. So here you have OH group, which is electron donor, and that is going to increase the electron density of the aromatic ring, and you have huge bromination of that phenol. Whereas your NO2 group is electron withdrawal, it makes the aromatic ring electron deficient, and therefore your meta position or carbon number 3 position is quite electron rich as compared to other carbons of the aromatic ring, and therefore we get bromination specifically at carbon number 3 position. So as for the reactivity of organic molecule is concerned, the electron availability at the site of reaction, as we have discussed two examples, carbon-carbon double bond or the carbons of the aromatic ring, that electron availability at the site of reaction in the molecule going to affect on the reactivity of that particular molecule. Either your reaction is going to be slower or faster, that is going to depend upon the availability of electron at that particular site of the reaction. And this is actually the structural effect. Means on the basis of what is the structure of your molecule, based on that you have either your substrate is electron rich or electron deficient, or at that particular site of reaction you have either more number of electrons available or less number of electrons available, and based on that you have different reactions at that particular molecule, and therefore this type of effect is what we call structural effect. Those structural effects are very important as far the organic reactions are concerned. Now we will discuss in detail one by one. First, the first effect is the inductive effect. Inductive effect. So this inductive effect is playing very important role in organic chemistry. Let us consider homoatomic and heteroatomic molecules like H2, Cl2, Br2. Those are the homoatomic molecules. Then HCl, HBr are the heteroatomic molecules. Right. So when you have homoatomic molecules, the electronegativity difference is not there because both are similar atoms. But when you have heteroatomic molecules, that time we have difference in their electronegativity. So here if you look at the HCl molecule, that Cl atom is electronegative and hydrogen is electropositive. So therefore here this electronegative atom try to acquire partial negative charge and electropositive atom acquire partial positive charge. So here we can have delta negative charge on Cl, delta positive charge on the hydrogen. Basically what is going to happen there, that Cl going to pull the electron pair which is there in between hydrogen and Cl bond. So that HCl bond electron pair is shifted towards the Cl atom, and therefore your Cl is going to acquire partial negative charge and hydrogen is going to acquire partial positive charge. As far as organic compounds are concerned, let's consider one example, CH3Cl. Here also we have CCl bond. Again, the carbon and Cl is having some electronegativity difference. So Cl is electronegative, more electronegative as compared to carbon. So therefore, this acquires delta negative charge, carbon acquires delta positive charge. And this is going to pull, that Cl is going to pull your electron pair towards the Cl atom. And therefore this carbon becomes electron deficient. As it has partial positive charge, it is electron deficient. Cl is electron rich. So this is, in case of heteroatomic molecule, there is such type of pulling of electron by your electronegative atom, and because of that the carbon or any other atom attached to the electronegative atom acquires partial positive charge. As a result, we get partial negative charge and partial positive charge on the atoms. That is, electronegative atom acquires partial negative charge, electropositive atom acquires, or the other atom, carbon or other atom acquires partial positive charge. Now, as far inductive effect is concerned, in case of organic molecules, that this inductive effect means the induction of polarization. As we come to know that this is what actually the meaning of polarization, that electronegative atom acquires delta negative charge, and other atom, carbon atom or any other atom like hydrogen or carbon acquires delta positive charge. This is what the polarization in the molecule. So induction of polarization in adjacent bond, induction of polarization in adjacent bond due to the polarization in one bond. This is the definition of inductive effect. Induction of polarization in adjacent bond due to the presence of polarization in one bond. So here suppose this is one bond between carbon and Cl. We have polarization here, having partial negative charge on Cl and partial positive charge on carbon, right? So here if you have some more carbons attached to this carbon, suppose we take one example here, CH3, CH2, 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 Cl. So here this is the bond which is polar, having delta negative charge on Cl and delta positive charge on carbon. So this is because of the pulling of electron by your Cl atom. So this carbon electron deficient. As this carbon becomes electron deficient, it tries to pull some electron from adjacent carbon in this fashion, and we have again generation of positive charge on this carbon. Again this is going to pull some electron from next carbon, we get again positive charge on this carbon. And similarly we have again pulling of electrons from the carbon-carbon bond, and we have again generation of positive charge on this carbon. So here the polarization in this particular bond induces the polarization in adjacent bond, and therefore other carbons are also going to be partially positively charged or electron deficient. This is what actually meaning of inductive effect, or this is the induction of polarization in adjacent bond due to the presence of polarization in one bond. Okay, so here this inductive effect is basically a polarization. Inductive effect is basically a polarization. Some important features of inductive effect is this effect is permanent. This inductive effect is permanent, and the inductive effect is going to operate via a sigma bond. It is going to operate via a sigma bond. Inductive effect operates via a sigma bond. Though it is permanent, it is having very small magnitude. Or magnitude of this inductive effect is very small, and this effect going to decrease with distance. This effect is going to decrease with distance. Like this, here when you are having this carbon is much more electron deficient as compared to this next CH2 carbon is, and then next CH2. So this is much more electron deficient, but it is quite electron rich as compared to this one. And this is again electron rich, or this is again electron rich. So and when you are having increase in distance, the magnitude of this effect is going to decrease. Now, as per the polarization, there are two types of inductive effects: electron donating inductive effect and second one, electron withdrawing inductive effect. Electron donating and electron withdrawing inductive effect. This electron donating inductive effect denoted by plus I, and this electron withdrawing is denoted by minus I. So here we are going to look over to the various groups or atoms responsible for electron donating and electron withdrawing in the molecule. So in organic molecule, those groups or atoms, when they are there in the molecule, they are going to either increase or decrease electron density. So depending upon that, we have classification of our inductive effect as electron donating and electron withdrawing. So let's look at that. When you have your alcohol RCH2OH, this oxygen is electron or electronegative atom, and it is going to pull the electron towards it. Whereas if you have oxygen with a negative charge, that time you have donation of electron from the oxygen to the carbon. Now here it is, suppose we say it is going to show minus I effect, and here it is going to show plus I effect. If you will look over the another one, RCH2 NH3. Here we have positive charge on the nitrogen, so it is much more electron deficient. Nitrogen is much more electron deficient. It pulls electron, so it shows minus I. Then, as we have already discussed, halogen atoms, when they are attached to the carbon, they are going to show minus I. Then, most of the alkyl groups, like suppose we have R, it is bonded to CH2 and something other group is there. So here this R, suppose it is alkyl group, it is going to show a plus I. R is going to show plus I effect. Also, when you are going to have different hydrocarbons like suppose RCH2, CH double bond CH2, then RCH2, C triple bond CH. Here this group is going to show minus I effect. This also going to show minus I effect. So this is why when you are going from this to this, here it is sp2 hybridized and this one is sp3 hybridized. Your alkene group is sp2 hybridized, alkyne is sp3 hybridized. So here percent of S character is more, and because of that there is minus I effect coming into picture. Now with this we are going to switch over the second structural effect, that is resonance effect or mesomeric effect. Resonance effect or mesomeric effect. Generally, when you are going to write the organic molecules, your organic molecule is oriented in different forms, or you have various structures for that particular molecule. So it is very difficult to explain the properties of molecule on the basis of a single structure. So therefore we need to write the various structures for that molecule, or we have to assign the properties of that molecule on the basis of the structures of that particular molecule. So here let us consider the structure of benzene. In the benzene we are having 6 carbon bonds, 6 carbon hydrogen bonds, then 3 carbon carbon bonds, single bonds, and 3 carbon carbon double bonds on looking at the structure of the benzene. So there are 3 carbon carbon single bonds, 3 carbon carbon double bonds, and 6 carbon hydrogen bonds. And the bond lengths, suppose the carbon carbon single bond, carbon carbon double bond, on the basis of this structure we can say that the carbon carbon single bond length should be 1.54 angstrom and carbon carbon double bond length should be 1.34 angstrom. But actually it was observed that the carbon carbon bond length in benzene is 1.39 angstrom. So all the carbon carbon bond length in benzene is observed 1.39 angstrom. And this is on the basis of X-ray crystallographic measurements, and it was observed that there is no either carbon carbon single bond or carbon carbon double bond type of bond length. It is in between that we have 1.39 angstrom. So on the basis of that structure come into the picture, that is we have not either carbon carbon single bond or not the carbon carbon double bond. So there is such type of structure coming into picture, and that is we called hybrid structure. This is hybrid structure of benzene, and this hybrid structure is because of resonance. This hybrid structure is because of resonance. So what type of resonance we have, or what is mean of resonance? Here in your benzene you have carbon carbon double bonds and carbon carbon single bonds. So there is resonance, means the delocalization of those carbon carbon double bonds takes place, and because of this delocalization, your carbon-carbon double bonds are not supposed to be on single place. It is moving from one place to another place. That means here we are having generation of carbon-carbon double bond here, and this position. So suppose we number the carbons 1, 2, 3, 4, 5 and 6. So here in your earlier structure we have 2, 3, 4, 5 and 6 one position, there is a carbon-carbon double bond. Now after delocalization we have a double bond positions like this 1, 2, 3, 4 and 5, 6. So the position of double bond is going to be changed. So it is not either at the carbon number or either at the carbon number 6 one position or either at the carbon number 1 2 position. It is going to be changed from one place to another place, and this is because of delocalization of carbon-carbon double bonds. And this carbon-carbon double bond means there are presence of two bonds, one is sigma and one is pi. So sigma bond is a stronger bond and pi bond is a weaker bond. So the electrons in the carbon-carbon double bond or the pi bond, those electrons are available for delocalization and they are going to delocalize from one place to another place, and therefore we have resonance in the benzene, and therefore we have actual observed bond length is 1.39 angstrom, and therefore we write the structure of benzene as hybrid structure. And from this concept of resonance come into the picture. Now, what is actual meaning of resonance? The resonance means the delocalization of pi electrons or non-bonded, or we can say unshared pairs of electrons over the unsaturated system. Delocalization of pi electrons or non-bonded electrons or unshared pairs of electrons over the unsaturated system. Generally, we take one example here. Suppose we have this aldehyde or alpha beta unsaturated aldehyde. Here we have this carbon oxygen double bond and carbon carbon double bonds. Now these pi electrons are going to delocalize in this fashion, and we are having generation of double bond here, oxygen negative charge, and the carbon become positively charged. So this is what delocalization of those pi electrons or this unsaturated system, and we can write the hybrid structure of this, that is this will have delta positive charge, this will have delta negative charge. So this is delocalization. Very simple example for delocalization of pi electrons. Another example we will take, that is, suppose we have phenol. The oxygen of phenol is having two unshared pairs of electrons. So here the unshared pair of electron is going to be delocalized over the aromatic ring, and we are going to have negative charge here, formation of C double bond O. Now oxygen will acquire positive charge, rest of the double bond remain as such. Again this negative charge resonated with the next carbon. We get negative charge here, double bond, then this is having positive charge. Again this negative charge delocalize. Again we get this negative charge. Now this negative charge is going to neutralize the positive charge of the oxygen. And we can write resonance hybrid for this. As we are getting positive charge on the oxygen, we will write delta positive charge on the oxygen, and here those carbons, suppose we number the carbons 1, 2, 3, 4, 5 and 6. So carbon number 6, carbon number 4 and carbon number 2 acquires negative charge. Carbon number 2, 4 and 6 acquires delta negative charge. So this is a resonance hybrid for your phenol molecule. Now here also we have classification of your resonance effect into two categories. One is electron donating and another one is electron withdrawing. So electron donating and electron withdrawing, two type of inductive effects are, resonance effects are there. So they are denoted by plus R and minus R. Electron donating is denoted by plus R, electron withdrawing is denoted by minus R. Here in this particular example of phenol, this OH group is going to donate the electron to the aromatic ring and makes this aromatic ring electron rich, as we are getting negative charge at carbon number 2, 4 and 6 position, and therefore this OH group is act as a electron donor. So this is coming under the substituent, which is going to show plus R effect. Let's look over to the another one example of the electron withdrawing resonance effect. The nitrobenzene we are taking into the consideration now. As such, in nitrobenzene, the nitrogen of this NO2 group is positively charged, so therefore it pulled electron density from the aromatic ring, and we have generation of positive charge on aromatic ring. We have generation of positive charge here, and rest of the carbon-carbon double bonds remain as such. Again, this carbon-carbon double bond neutralizes the positive charge by delocalization of pi electrons. We have generation of positive charge at this position, new carbon-carbon double bond here, this double bond remain as such, then O minus, and N plus SH. Now again another carbon-carbon double bond helping to neutralize the positive charge, and we have generation of positive charge at this position. Single bond O, this is negatively charged, and it is positive. Rest of the double bonds remain as such. We have new carbon-carbon double bond here. At last, we have neutralization of this positive charge on O minus, and we get the formation of now let us number the carbons 1, 2, 3, 4, 5 and 6. So because of the withdrawing of electron by NO2 group, we are getting the formation of positive charge at carbon number 6 position, carbon number 4 position and carbon number 2 position. Therefore, we can write the resonance hybrid of this nitrobenzene like this. You have NO, O, nitrogen as such, we have positive charge, so therefore we are putting the positive charge as such. Then we have generation of N double bond O, they are getting negative charge, so therefore delta negative. At carbon number 2, 4 and 6 position we are getting positive charge, so therefore they are delta positively charged. And this is the example of the substituent which is going to show electron withdrawing resonance effect. So it is an example of minus R. This NO2 group is going to show minus R effect. So there are a number of substituents available are going to show plus R or minus R. So we have discussed here two examples. One is going to show plus R effect, that is OH group in phenol, and one is going to show minus R effect, that is NO2 group in nitrobenzene. And one example we have written earlier, that is the C double bond O group, this one. This carbonyl group is also going to show minus R effect, generates the positive charge on this particular carbon. So this is the example of minus R, this is the example of plus R, and this is also example of minus R. To identify or to understand how the substituents are going to increase or decrease the electron density on aromatic ring. So here in phenol, OH group is going to increase the electron density on aromatic ring, and your NO2 group is going to decrease the electron density on your aromatic ring. We just going to have some more examples of the substituents. Those are going to show plus R and minus R effect. So let's look at that. So first we will have plus R, or the groups which are going to show plus R effect. Suppose we have O minus, Nr2, OH, SH, SR, FCl, Br, I. Those are the different substituents which are going to show plus R effect. Let's have some substituents going to show minus R effect, as we have discussed here. NO2 group, then SO3H, SO2R, carbonyl, either aldehyde or ketonic group, or ester, and cyanide or nitrile, and carboxylic acid group. Those are some examples of the substituents going to show minus R effect. So, as per resonance effect discussion, we have to take into the consideration of few important things. That is, as we have written here, those are the two different structures. Here we have number of structures for NO2 groups. So those, suppose this is, we are going to say first, second, third, fourth, and fifth. Those are different resonating structures. Those are different resonating structures or canonical structures or canonical forms. Those are different resonating structures or canonical forms, and this arrow is put in between every structure. This arrow is the resonance arrow, or arrow used to show different, or used to separate different canonical structures or different resonance structures. This arrow is put there, and this is one of the important part of writing a resonating structure, that is writing of this double-headed arrow in between two different canonical structures. So this is a resonance arrow. We are writing in between two different resonating structures. Okay, so that is what about the resonance effect. We will discuss some more details about this resonance effect in next part of our video. In this video, we learn about what is the meaning of structural effects, how the structure of molecule is responsible for the reactivity of that particular molecule. Then we come to the first structural effect, that is inductive effect, that is induction of polarization in the molecule. We have discussed about two types of inductive effects, electron donating and electron withdrawing. Then we go to the resonance effect. Again, here we have two types of resonance effects, plus R and minus R, that is electron donating as well as electron withdrawing. And also we have come to the understanding about how those effects are going to increase or decrease the electron density at the site of reaction. And also we have discussed about the various groups or substituents which are responsible for electron donating resonance effect or electron withdrawing resonance effect. Thank you.